Hello everyone, welcome to this next video on field theory. In this video we shall see the cyclotomic polynomials. In the previous videos we have seen several tests of irreducibility, right? And moreover we saw that cyclotomic polynomials are irreducible polynomials in the last video, and we have given the proof using Eisenstein's criteria when n is prime. So in this video we shall see what are these polynomials and how can we calculate these polynomials, right? So if we are given any positive integer n, then the nth cyclotomic polynomial, this is the unique irreducible polynomial with integer coefficients. It has integer coefficients, it is irreducible polynomial, this is unique polynomial. Moreover, that is the divisor of this polynomial x to the power n minus 1, and it is not a divisor of x to the power k minus 1, where this k is less than this n, right? Suppose this polynomial divides x to the power 3 minus 1, so it would not divide x to the power 2 minus 1, and it would not divide x to the power 1 minus 1, right? So this is what they are saying. So now what does it mean that this polynomial is a divisor of x to the power n minus 1? So suppose we are to find the root of this polynomial x to the power n minus 1, that means we are looking for n, right? So x to the power n is equal to 1, or we are looking for n which is equal to 1 to the power 1 by n. That means we are looking for the nth roots of unity for this case. So you must be knowing what are the nth roots of unity. Likewise, you might have studied in complex analysis that the nth roots of unity, they are given by this e, that is exponential raised to power 2 pi iota k upon n, where what is this k? This is also a positive integer, right? And it is less than or equal to n. That means if n is 3, so it could be 1, 2, 3, right? So we can have a look at example. To understand this nth roots of unity, we'll consider x cube minus 1 is equal to 0. So we are looking for all those x which is equal to 1 to the power 1 by 3. That is the third root of unity. So in this case, according to this formula, so our n is equal to 3, therefore k is equal to 1 to 3, right? So according to this formula, we have e to the power 2 pi iota, k is 1, then k is 2, then k is 3 divided by n. So we have 3 roots, right? And by De Moivre's formula, you know, e to the power iota theta, this is equal to cos theta plus iota sin theta, right? So we have implied the same thing. So it is equal to 2 pi upon 3 into iota. So this thing could be written as cos into 2 pi upon 3 plus iota into sin 2 pi upon 3. Similarly, over here with iota we have 4 pi upon 3. So it is cos 4 pi upon 3 plus iota sin 4 pi upon 3. Likewise, it is cos 2 pi plus iota sin 2 pi. So now you know sin 2 pi is equivalent to 0. This cos 2 pi is equivalent to 1. So this root becomes simply 1. What about these roots? So cos 2 pi, you might be knowing from trigonometry how to solve these, right? Cos 2 pi comes out to be minus 1 by 2. Sin 2 pi by 3 comes out to be root 3 by 2. So this root becomes minus 1 by 2 plus iota square root 3 by 2. And the second root, cos 4 pi by 3, it comes out to be minus 1 by 2. And sin 4 pi by 3, it comes out to be minus square root 3 by 2. Therefore, we have these 3 roots, right? So this polynomial x cube minus 1 could be written as the 3 polynomials x minus the first root, x minus the second root, and x minus the third root, right? Or generalizing this, we can write this as x minus the root, x minus the product of x minus the 3 roots, right? Where what is this k? This k is varying from 1 to n. And what is n here? N is 3 basically in this case. For x cube minus 1, we have n as 3, right? So basically you can write any polynomial of this kind as the product of this. And when do we call such a polynomial? Now you saw that you can write any polynomial of this form as a product of some polynomials, where you write these polynomials as x minus some root of unity, right? So now when can you call these polynomials as cyclotomic polynomials? When? So by definition, there is one thing that we are lacking. It should not, whatever the coefficients you are writing, the product polynomials you are writing, they should not divide some lower factor of some lower power of x, like x to the power k minus 1, right? So let us understand it in this way. So the cyclotomic polynomial phi 3x, what would be that? It would just be the product of, obviously this polynomial should divide this, but it should not divide x square minus 1, and it should not divide x minus 1, right? So it should divide this, but it should not divide this and this. So that means we are left only with these two polynomials. And when you multiply these polynomials, so it would be x, you can just open this bracket, so you'll get x plus 1 by 2, and here you would get minus iota square root 3 by 2, right? And here you'll get x plus 1 by 2 plus iota square root 3 by 2. So now you can simplify this. It would be x plus 1 by 2 square minus, right? So a minus b and a plus b, right? So we have a square minus b square. So it would be iota square root of 3 by 2, it would be 3 by 4. So iota square, it is minus 1. So this would become plus. So we have plus 3 by 4. And here we would have x square plus 1 by 4, right? And then we have x, just opening a plus b whole square, so it would be a square plus b square plus 2 into a into b, right? So this thing, so we have x square plus x plus 1. So this is the cyclotomic polynomial phi 3 of x. So we'll just verify this in a moment, right? So generalizing the cyclotomic polynomials, by definition we need those roots of unity, those e to the power 2 pi iota k by n, where k is positive integer, k is less than n as in the previous case, and k is co-prime to n. So here that means the GCD of k and n should be 1. So those factors are included in this cyclotomic polynomial. So for example, here we had n is equal to 3 and we had k is equal to 1, 2 and 3. So the only k which are co-prime to n are 1 and 2, right? So the factors that we have used corresponding to k is equal to 1. So this factor corresponding this one and this factor. So when you saw when you have multiplied these two factors, you have obtained the cyclotomic polynomial. So this is the necessary condition to obtain a cyclotomic polynomial. So generalizing this definition, as we have written for the roots of unity, right, this one, we now have one extra condition, that is GCD of k and n should be 1 in addition to all these things. So the cyclotomic polynomials could be written as the product of these polynomials, where what are these? These are the nth roots of unity. Moreover, these are primitive nth roots of unity. Primitive means the GCD of k and n should be equal to 1. So now for integers n varying from 1 to 30, the cyclotomic polynomials are written like these. You can have a look. All the coefficients here are either 1, minus 1, right? And in some cases the coefficients here are 1, minus 1 or 0, right? You can see. Moreover, there are two formulas for special cases. When n is given to be prime, in that case we have phi n x, which is equal to the summation x to the power k. So let us have a look. 2 is prime, therefore it should be k varying from 0 to n minus 1. So it should be 1 plus x to the power 1. 2 minus 1, that means it is equal to 1. So x to the power 1. So 3 is also prime. So it should be x to the power 0 plus x to the power 1 plus x to the power 2. We will go up to 3 minus 1, n minus 1, right? So again 5 is prime. So we have 1 plus x square plus x cube plus x raised to power 4. We will go up to 5 minus 1, that is 4. Again for 7 we have this thing, again for 11 we have this thing, for 13 we have this thing, and so on, right? And when n is equal to 2p, where p is some odd prime number, in that case you can write the polynomial as minus x raised to power k, where k varies from 0 to p minus 1, right? For example, you have phi 4. Here you can write this 4 as 2 into 2, right? So p in this case is 2. So therefore your polynomial would be, p should be odd prime. So we cannot take this case, right? It should be an odd prime. We can take this case. So 6 could be written as 2 into 3, where this 3 is a prime number and it is also odd, right? So therefore you can write this as summation k varies from 0 to p minus 1, 3 minus 1 minus x raised to power k. So it should be equal to minus x raised to power 0 plus minus x raised to power 1 plus minus x raised to power 2. So it is equal to 1 minus x plus x square, right? So you can calculate some of these like these, and there are also various methods to calculate these polynomials. Now the main formula here is what is the relationship between these cyclotomic polynomials and the primitive roots of unity. As we have seen, the primitive roots of unity are given by this polynomial x to the power n minus 1. This is equal to pi phi dx, d divides n. So now it means we can write this as product of polynomials x minus a, x minus b, and so on, right? Where these a, b, these are the nth primitive roots of unity. Moreover, these roots here, d should be a divisor of n. What is the given power n here? D should divide that power. So we'll take only those cyclotomic polynomials where this d divides n. So for example, we are talking about x to the power 15 minus 1. So in that case, our cyclotomic this could be written as the product. Now d divides 15. So what is d? D should be 1. It should be 3. It should be 5. It should be 15. So we would have phi 1x multiplied by phi 3x multiplied by phi 5x multiplied by 5 phi 15x, right? So this is the thing. So this is a result. Moreover, these polynomials are irreducible polynomials as it is given in the definition. So this proof in general was given by Gauss, and when n is prime, it is given by Eisenstein's criteria, and we have already proved this thing, right, using the Eisenstein's criteria in the previous video. Now the last thing that I wanted to talk about is the degree of this polynomial phi n x. It is given by a function phi n, which is known as the Euler's totient function or Euler phi function, denoted by this phi. And how do we calculate this phi of some integer n? It is calculated by calculating all the positive integers which are less than n and which are relatively prime to n. So that means we are looking for the number of k's such that the GCD of k with n is equal to 1. So how many that many k's which fulfill these condition, they are counted and they are equal to phi of n, right? For example, we are calculating phi of 3. So the numbers 1 and 2, they are relatively prime to 3, right? 3 is not counted because the GCD of 3 with 3 itself is equal to 3 and it is not equal to 1. So the only numbers that we have is 1 and 2. So counting them, it gives me 2. So phi of 3 is 2. Phi of 4 is again 2 because the numbers less than or equal to 4 are 1, 2, 3 and 4. But the GCD of 2 with 4 is 2, which is not equal to 1. And the GCD of 4 with 4 is equal to 4, which is not equal to 1. Therefore, we have only 1 and 3. So 2 in total. Again, phi of 5, this is equal to 1, 2, 3 and 4 because the GCD of 5 with 5, that is equal to 5 and it is not equal to 1. Therefore, these are total 4 in number. So we have phi of 5 as 4. Similarly, phi of 20, it is equal to 8 because these are the only numbers which are relatively prime to 20, right? So in this way you can calculate this. Moreover, here you may note that this is prime number. So you have phi of any prime number p, this is equal to p minus 1. Because every number which is less than p is relatively prime to p. That is by the definition of a prime number, right? You can find more about this Euler-Totian function in number theory subject, right? So that is it for this video. I hope that is interesting. Thank you for watching.